we go with our last day of solutions. And really all we're going to be doing is talking more about colligative properties, but we're going to be able to figure out the molar mass of our substance. And if it's a molar mass, chances are we're talking about the molar mass of our solute. And we're going to do this by freezing point depression or boiling point elevation. So in theory, if we were back in lab, and by the way, you guys will be doing something like this in your next lab, if we knew some freezing point or boiling point data, we could use that information to come up with what the mass of that solute is, the molar mass of that solute. So as far as the our steps that we're going to be taking, we're just going to be using our formulas, either the change in boiling point or the change in our freezing point, and from there we want to calculate our molality, because we know that within molality we have moles of our solute, that's what we're going to be concerned with, divided by kilograms of our solvent. So we can use that information to go ahead and get just the mass of our solute, or moles of our solute, and then we can, of course, get molar mass by saying that's equal to grams divided by moles. So that is our plan, and here we go. Okay, so the first one, and again, you gotta identify your variables. You gotta think about which one's the solute and which one's the solvent. So we know that pure benzene freezes at this temperature. I don't even need to read any further. What is benzene in this case? Solvent. So here we have our solvent, and we have an unknown solute that we need to figure out. We know that it is dissolved in so many grams of benzene, and we know the grams of that as well. Now our new solution, once we make this solution, we put that solute into the solvent, it doesn't freeze at 5.5 degrees Celsius anymore. Instead it freezes at 1.44 degrees Celsius. So what we want to do is determine our molar mass of the solute. I know that I'm going to use this formula. We're talking about freezing, is that right? Yes. So here is my formula. What is the first thing you guys want to do? What should we calculate first? Before that. The what? Change in temperature. I would think that would be the best way to go with this. So we know that benzene normally freezes at 5.5 degrees Celsius. But now, instead, it's going to freeze at 1.44 degrees Celsius. So we do a little bit of quick math, and you could write this down, or you could just calculate it. It doesn't matter. And remember, we're just worried about our positive changes is all we really have to worry about. So the absolute value of it. And we get 4.06 degrees Celsius. Okay, so we have got our temperature is thrown in there. Now, the next thing we want to do, and you don't have to do it in this order, but again, I just kind of follow lots of times the formula that's given to me. I see the next thing is I. Do I know my I in this case? All it tells me is unknown solute. Yesterday we talked a little bit about some things that you might see. You might, if you ever see the term, you have an organic solute, or a non-volatile solute, or a non-electrolyte, or a covalent substance, or a molecular compound. All of those are going to be that your I equals 1. It does not break down into ions. Really what you have to do here, because it's unknown, it doesn't give you any other information. You just have to assume that I equals 1. It's a big assumption, but we just have to assume it's some sort of molecular compound, unless you're told otherwise. So I'm going to go ahead and plug in a 1 here. My K sub F value is given to me. I know that that's going to be for my solvent, which is benzene in this case, so I can write that down. 5.12 degrees Celsius per molal. And then there's my missing variable, is the molality. So I change it all around, and I solve for my molality. Did I get an answer? Perfect, 793. So that is going to be moles, and that's moles of my solute. I don't really need to write all this out. I'm just doing this to make sure that you guys understand this is for my solute. Well, molality is going to be moles of solute divided by kilograms of solvent. And of course, this is just a 1 right here. So that's what we've got. That's kilograms of our benzene. So what should we do next? What do we need to get rid of? The kilograms. We don't really care about our solvent. Remember, we want to find molar mass of our solute. So if I want to get rid of my kilograms of my solvent, which is benzene, I am going to find that I've got 75.8 grams of my solvent, my benzene. So I'm going to take that and change it around to kilograms. That's of my solvent. So now that goes away. And when I do my math, I'll have my answer just as moles of my solute. Now, instead of really being able to efficiently be able to work through my dimensional analysis and keep going with this, remember that I ultimately want to find molar mass, and we know that molar mass is given to us as grams. That's a funny looking G. It's given as grams per mole. So I'm going to have moles in my numerator, so really the easiest thing to do is just go ahead and get an answer and do this in 2 steps. So when you get an answer, you get 0.0601 moles. So the easiest thing to do is just now take a different step down here, and you know your grams. What's your grams going to be? Anybody see it up there? Good. So we've got 10.9 grams of our solute divided by 0.0601 moles of our solute. So that will give us the molar mass of our solute, because that's what we're looking for. And the final answer is 181 grams per moles. While you're finishing that up, I am going to jump back to here because this was just brought to my attention. I kind of skipped right over this. That in our formulas here, I was accidentally left out. Again, that's called Van Hoff's factor. That's the number of particles that your solute breaks into. So don't forget about I. That was just inadvertently left out. Okay, number 2. Are we good? Okay, number 2. We have a solution was made by dissolving so many grams of a non-volatile solute in 104 grams of acetone. So you should be able to look at this and know that acetone is your solvent. The solution boiled at 56.58 degrees Celsius. The boiling point of pure acetone is 55.95 degrees Celsius, and the Kb value for acetone is also given. We need to calculate the molar mass of the solute. So we're going to set it up just the same. We're talking about boiling. So this is our formula. Let me stop for a second and bring something up with what's given to you in your problem. When you start looking at your homeworks, you're going to find a lot of this stuff is not given to you because there's no need for this information to be given to you, the normal boiling point of acetone. There's no need for this information to be given to you because that's the type of stuff that you would look up on that little half sheet, your little reference sheet of your K values and your boiling and freezing points that was given to you. So the key is that you have to know to look it up for acetone. That's your solvent. So that's what you need to look it up for. But here it happens to be given all in the problem. So again, I would go ahead with the first step that we did last time, which was what? What should we calculate? Change in temperature. So we know that it normally boils at 55.95, but now it's boiling at 56.58. It's elevated, right? So our difference is going to be, we subtract that and we get 0.63 degrees Celsius. I see this word right here, it just says a non-volatile solute. So I just look at that and say, okay, well that's telling me that it's got to be 1. We're just going to go with 1. When in doubt, just use 1 unless you're specifically told some information about how many particles they break into. Our KB value we would look up on our half sheet. Here it happens to be given to us as 1.71 degrees Celsius per molal. And we're solving for the missing variable of molality. So molality is going to be equal to 0.368 moles per kilogram. I don't really care about the kilograms. That has to do with my solvent. So we want to get rid of the kilograms. So we need to multiply by what number? Okay, good. 0.1040 kilograms that I found right up here because that was for my solvent. So now I get rid of my kilograms and all I have is moles of my solute. So the answer here is 0.0383 moles. Now it's easy. All I have to do is say, well, I'm starting off with 3.75 grams of my solute, and I know that in those 3.75 grams I've got 0.0383 moles, so my molar mass is going to be equal to 3.75 grams divided by 0.0383 moles, and we get the mass equal to 97.9 grams per mole. And we have one last one. Okay, again, these are all pretty much the same. This is asking something a little bit different at the end. It says we start with so many grams of a sodium halide salt. Well, that looks a little different. It's telling me a sodium halide salt. That's going to help me determine something. And it was added to 100 grams of water. It was found that the solution froze at this new temperature. What is the formula? Not only what is the mass, but what is the formula of this compound? So we're talking about freezing. So here's our formula. Let's start with the first thing we've been doing, which is our change in temperature. How do we figure out that one? We're only given one value. Okay, good. So water normally freezes at 0. So you have to look at this and say, there's my solvent. And if it was something else, if it wasn't water, you would just look it up. But you know water freezes at 0. So if the new freezing point is this temperature right here, the difference would be 0.868 degrees Celsius. Okay, next one's a little trickier. We want to find the I value. We want to figure out the number of particles that our solute breaks into. What do we know about our solute? It's a sodium halide salt. What does that mean? Sodium plus what? What is it? Plus a halogen. So if you look over there at your periodic table, think about those charges. You know your sodium is a +1. What's your halogen's charge? -1. So what does that mean? How many particles is it going to break into? 2. So we've got 2 particles that it'll break into. Okay, sub F. Uh-oh, I don't see that written there. What should I do? Look it up on the half sheet. So we look it up. And we find 1.86 degrees Celsius per molal. That's for our water, because that's our solvent. And then, again, we do not know our molality, so that's what we're going to solve for. Molality ends up equaling 0.233 moles per kilogram. That's what everybody should have calculated there. Next step. We don't care about our solvent, so let's get rid of that information, meaning I should multiply it by what? 0.1. And I really can't stress this enough that so many people are still missing that. If you have 100 grams, that's 0.1 kilograms. Don't just move it 2 places, move that decimal 3 places. So I'm still seeing quite a few people miss that. So we've got it now as our moles, and that's going to equal 0.0233 moles. So last step is easy. Molar mass is going to equal the mass that I start with in grams divided by the moles of that substance, which gives us an answer of 150 grams per mole. There's a decimal there to make it 3 sig figs. So we really haven't answered the question. The question is, what is the formula of this salt? What are you going to do? What do you think it is? We know it's sodium. It's a sodium halide. So sodium iodide. So you know that your mass is 150, your molar mass is 150. Subtract the mass of your sodium, and what's left over would be iodine. So sodium iodine. Iodide is your answer. That is all we have for this unit, so test is around the corner. Bye.